The last of our statements or corollaries that have to do with right triangles is LA, which stands for leg and angle. So remember, if you have two right angles, they already share a common 90-degree angle. So let's start with triangles ABC and DEF having the usual correspondence among the points. And then if the measure of angle B and the measure of angle E are both 90 degrees, as I've noted here, and the measure of angle C is congruent or equal to the measure of angle F, that means we have this angle and this angle congruent. And then we have the side AB congruent to the side D. Let's see, AB, it should be DE. Make that correction right there. ABDE. Then these two triangles are congruent. Triangle ABC is congruent to triangle DEF. Now notice this is a special case of angle, angle, side. Angle, angle, side, angle, angle, side. But since we knew they were right triangles, you only need the one additional angle. All right, let's move on to the next corollary, which is SSA, but notice the capitalization. You have S, big S and little s, and it corresponds to a big side and a littler side, and then the angle. So let's take two triangles, ABC and DEF, which we've got pictured here, in the usual correspondence among the points, ABC to DEF respectively. If AB is congruent to DE, we can mark that as such. And BC is congruent to EF. Let's mark that with 2 notches. And angle A is congruent to angle D. So mark those as congruent. And here's the kicker. Side BC is bigger than or equal to side BA. Oh, this one. Side BC is bigger than side BA. And you can see as I made these diagrams that that is the case. If all of that is true, then we have two congruent triangles. Triangle ABC congruent to triangle DEF. So that's an SSA that does work. So you have a big side, a little side, and an angle. All right. Oh, one more comment about this. Remember what additional information we know about when we are told that the side BC is at least as big as AB, then the angles opposite those sides are in the same relationship. The side opposite BC, which is angle A, is going to be greater than or equal to the side opposite AB, which is angle C. All right, let's move on to number 8. An example here. What we've got to draw is two concentric circles with common center O. So do your best to find the center of that circle, and we'll call it O. And then draw another circle, smaller than the big one, best you can. So now we have two concentric circles. They both have center O. On the smaller circle, draw two distinct radii, OA and OB, and for our purposes, let's do something like this. Put them fairly close to each other to make the drawing easier. That will be our point A, and that'll be our point B. Okay, so now that gives us two line segments, radii of each one is a radius of the smaller circle, OA and OB. Now, on the larger circle, label the points C and D such that the angle of OAC and the angle of OBD have the same measure. So let's do one of them like this. OA, and that'll become C. So what we need is this angle here, this angle A, to be the same as the angle B when I draw here. So now I've drawn them to be the same. That angle A is the same as or equivalent to the angle B. All right, now we need to prove that the two line segments AC are the two line segments AC and BD are congruent. Those last two that we drew. Okay, this will be pretty simple. All right, OC, which I haven't drawn the segment, but let's go ahead and draw that segment. OC and OD, this is the point D, and OD are equal to each other. Why is that? Well, it's pretty straightforward. They are both radii. Each one of them is a radius of the same circle. And those two are both bigger than OA and OB. And OA and OB are equal to each other for the same reason. They are both radii of the same smaller circle in that case. So triangle OAC is congruent to triangle what? OAC will be OBD. And why is that true? Well, that's true by big side, little side angle that we just proved above. We've got this side, CO, followed by a smaller side, OA, and then an angle. And that's this big side, OD, then a smaller side, OB, those are equal, and then followed by the angle. So we have two equivalent triangles. If we have two equivalent triangles, then corresponding parts are congruent. So AC, that length, is equal to the length of BD by our usual corresponding parts of corresponding figures are congruent. And maybe I'll mark SSA. The two triangles would be segment OC, segment OD, OCOD, and then the small side would be CA and CADB, and then angle A and angle B. This just stands for angle. This is specifically the angle A in the diagram and then the angle B in the diagram. Okay, we're going to finish this video with just a couple of definitions. The distance D from a set to another set. Well, all it is the infimum of the distance from A to B, little a to little b, where little a is in the first set and little b is in the second set. So you may not remember what infimum means, but it's the least upper bound. So for example, how far is this? Let's draw this picture first. Here's the real line. And let's go put 0 here, put 3 here, and maybe 7 here and 10 there. So we want to know Here's the first set. That's the open interval from 0 to 3. And here's the open interval from 7 to 10. If you like, you could put circles here on each one of the endpoints, open circles. So if you take a point in here, say 1 and 9, the distance from 1 to 9 is 8. But what I'm looking for is the smallest possible distance between a point in here, say 8 and 2. Now we're down to 6. 7 is not in this set. 3 is not in this set. But 7.00001 is, and 2.99999 is. So the number we're looking for is going to be the limit. Pretend like you're approaching 7 from this direction, and you're approaching 3 from this direction, so you can get as close to the numbers 3 and 7 as you want to. So you might have figured this out already. It's quite simple. The infimum of that is going to be 7 minus 3, which is 4. There's no bigger number you could use, and there's no smaller number you could use. So the distance is 7, and it would be the same if this were a closed interval. If it included 7 and this one included 3, or if one of them were included, the answer would be the same. The distance is 4. But the more important one we're thinking about is, how do you find the distance from a point P to a line? So you've got a line L and some point P that is not on the line. So maybe put the point P right there. Well, you might be able to say, well, I could measure this distance right there, measure that, and that's the distance. No, when you say distance, it means what is the smallest distance from that point to any point on the line. So what are we looking for? We are looking for the distance where the line, where the point P, draw the line segment, L being some point on this line, capital L, and it needs to be perpendicular, like that. That would be the distance between the point and the line. You don't have to say the perpendicular distance. If you say the distance, it's implied. What is the shortest possible distance? And it will be the perpendicular distance.